So, hello student to the Foundation of Classical Electrodynamics course. So, today we will have lecture number 11 and today we will going to understand the curl operator and Stokes theorem. Okay. So, before going to the curl operator, so let me once again, so today is lecture number or class number 11. Okay. So, before going to the curl, the concept of curl of a vector, let me remind what we did in the last class. So, in the last class, in the very end part, we defined this operator and we mentioned that this is called the del square operator and it operates like this. I can have a gradient of a function phi, and if it operates over phi, so this is the operation one should find, one should get. So, this operator at the end of the day gives you the second order derivative. So, let us now quickly, I give you as a homework, but let me do it quickly. So, what is this? If I find out the the gradient of a scalar field in Cartesian coordinate, let us consider ourselves in let us consider this is a Cartesian coordinate. So, phi is a scalar field x y z and this is a scalar field. So, I am operating this over phi. So, what I will get? I will get I del phi del x plus j del phi del y plus k del phi del z. This I will get, right. Now, the next phase I want to find out these things, divergence of this quantity whatever I am getting here, divergence of gradient of phi. So, I know the recipe when we say the divergence. So, I should have I del x plus j del y plus k del z and then dot the rest of the term, which is I del phi del x plus j del phi del y plus k del phi del z. Now, eventually we will get that when I will going to operate over I mean this is a dot product. So, I can have simply I can have this one. So, del 2 of phi del x square plus del 2 of phi del y square plus del 2 of phi del z square. So, this is the operation we can have. Okay. Now, this operator is this operator has a name and we called it this operator as Laplacian. Laplacian operator. This later we find that we have a profound implication of this operator. In different cases we will going to get this fundamental operator and how it works we will going to check. But at this moment also I like to mention here that this operator can operate over phi, which I know that it is giving like d2 phi dx square, where phi is a scalar field, d x square plus del 2 phi d y square plus del 2 phi d z square. Here phi is a scalar field. But this operator can also operate over a vector field, and in that case it is simply d2 vector A, which is a function of x, y, z, and I am having x square plus y square z square. Now, this is a scalar operator, mind it, this is a scalar operator. Unlike the del operator, this is not a vector operator, this is a scalar operator, and eventually this operator gives us del 2 del x square plus del 2 del y square plus del 2 del z square. So, that means it can operate over a scalar field, and it can also operate over a vector field. When it operates over a scalar field, the end result will be a scalar. When it operates over a vector field, the end result will be a vector. That is all. So, this is roughly the the way this Laplacian operator operates. Later we will discuss more about this operator, what is the form of this operator in other coordinate system, very important. Mind it, this is in Cartesian coordinate system. So, this is very simple, but for other coordinate system like cylindrical coordinate system and spherical coordinate system, it is not that easy. So, we need to check this and we will going to find out. Okay. So, now the today's thing that we quickly like to understand is the curl of a vector function. Vector function or vector field. So, curl of a vector field, that is the next topic we like to explore. Well, let me first define how curl is operated. So, curl is an operator, it operates over a vector field, this is a vector operator, and that over a vector field, and it operates like this, like a curl. So, here I like to put I like to put any vector I, j and k. Here it will be the operator del x, del y and del z, and finally I have the component of the vector field Ax, Ay, Az. Okay, and this should be a vector quantity. This should be a vector quantity. Unlike the divergence, the end result of the curl is a vector quantity. Now, here I mean you should quickly write what is my del operator. This is I del x plus j del y plus k del z. This is the partial shorthand notation of the partial operator, partial derivative, and my A is simply Ax I plus Ay j plus Az k, and I put it here like a cross B form. Okay. Now, what is the ith component? We know how to deal with this. So, and this is called curl of the vector field A, and the ith component will be simply epsilon I j k, and then we have del a k del x j. Now, here x j is when x j stands for x, y and z with the indices 1, 2, 3. So, that means what I am trying to say is this is x 1, this is x 2 and this is x 3. This is the way we define j is equal to 1, 2 and 3. Okay. So, this is the way one can operate this curl operator over A, and we will get this vector quantity. Now, the question is what is the geometrical interpretation of that, and that basically this operator basically tells us that how curly how curly the vector field is. So, I will like to show here once again this figure of this vector field that I mentioned in the last class, that here you can see that a vector field, this last one V x equal to y I plus x j, you can see that there is a, you can see apart from other, I mean from these two x, the first one and second one, it is having a natural curliness, and this natural curliness you can measure with this curl operator. This curl operator tells us that how curly these vector fields are for a given point. Here if you calculate, you will find a non-zero value, and that tells us that this vector field is curly, and what is the amount of curliness gives us by the magnitude, because when you calculate the curl of a vector, so it eventually gives you a vector quantity. So, that means you have a magnitude and direction, and the direction will gives you the, because this is a curliness, so it is a vector quantity. So, it gives you the direction as well as the magnitude, and this magnitude will tell us that how curly the vector is. Okay, we will come to this in detail maybe later, but let me whatever we have, so let me write it down, that curl of A geometrically, or if I want to understand physically what it is doing over a vector field. So, curl of A, this quantity is basically a measurement of it is a measurement of the curliness or another word twist, how twisted it is. Twist of the given vector field. A at some point, at some given point. Okay. So, so that means in the bottom I can write, so a vector field, if a vector field is given to you, this is given to you. Okay. So, two way you can make a treatment, there are two way. You can calculate the how divergent it is by calculating the divergence of this vector, and if you find there is a for a given point, you can calculate this value is non-zero or not. If you find this is a non-zero value, that means this vector field has a divergence at this given point. Or you can also find out how curly it is for a given point, at a given point with this operation. So, A is a given vector field, and with these two operations, one is called the divergence and another is called the curl. You can measure how the vector is spread out, how much it is spreading out, how diverge it is, or how twisted it is. These two measurement you can do. Okay. Later we will do more problems and then maybe you can understand. So, this is a given vector field. This is a given vector field, and you can measure these two quantity. As soon as it is given, you can measure these two quantity. And the divergence and curl are two very important properties of a vector field that we will going to use later, and these theorems are also very important. So, now we will going to introduce another theorem which is again very important, and this theorem is called the Stokes theorem. Okay, the mathematical statement of the Stokes theorem, let us try to understand. Let me write down first the mathematical statement, and it says that if I am calculating a surface integral of a curl of a vector field over a surface, that quantity is eventually the same value we are calculating if I am having a closed line integral and then this vector field over this given line. And what is the line? The line which is encircling the surface. That means, if this is my surface, suppose let me draw it, suppose this is a arbitrary surface and I am calculating the curl of A, I calculate, and this is a vector quantity, and then I calculate the flux of this quantity over the surface, right. This is a surface integral. So, flux is nothing but this is a vector quantity, and this vector quantity, if I make a dot product with S and then integrate, so what we are getting is the flux. So, the total flux, if I calculate for this given surface, that value is equivalent to, if I only calculate the line integral, the line is this one, it is encircling the entire surface, this is the line integral. So, this closed line integral, and if I simply calculate the given vector field over this line element. Okay. So, that is the statement. So, first I am doing the curl and then make a surface integration, whatever the value I am getting, this is a scalar quantity, you can see that. Then I integrate the line integral of the line I choose is such a way that it is encircling the entire surface, that is all, that is the mathematical statement. Well, geometrically, if I want to understand before going to a rigorous proof, it is quite nice. And so, this is the geometrical interpretation of this statement if I want to find out. So, in geometrical interpretation I can say that, okay, let me have a surface like this. This is a surface element I am having, and over the surface element, over the surface I am having a surface element, a tiny surface here, and I calculate and the n is say along this direction. This is the unit vector of the surface, and I am calculating that quantity, this quantity, integral of this curl of A whatever and dot ds, right, dot ds. Okay. Now, if I now make a subsection of this entire surface here. So, let me draw the surface once again. The same surface I am drawing here. Now, I am integrating with small surface area, right. This is the small surface area. So, that means eventually I can divide this entire surface to different sections. Okay. These are the small DSS that will add and make a complete surface, and for each surface I am calculating this quantity curl cross A, and curl cross A is basically gives me the curliness of the vector field. So, eventually what I am getting is I am getting this kind of curliness here, and that we are measuring. Each section I am having a curl. So, curl is basically gives me the twist, how twisted it is. So, I am calculating this twist at each delta S surface. So, everything is delta S. Now, if you look carefully, you will see that if I, so there is a cancellation. So, if I go to the boundary with this twist, I will have this. These are the boundaries. Okay, and it is going in this direction, this direction. For this case, it is going this direction, this direction, this direction, this direction. For this case, it is going this direction, this direction, this direction, this direction. And for this case, it is going this direction, this direction, this direction, and then this direction, and this direction. For and here we have this direction, this direction, this direction, this direction, this case, this direction, this direction, this direction, this direction. In this case, it is this direction, this direction, this direction, this direction. In the lower case, it is this direction, this direction, this direction, this direction, this direction. I am just drawing the direction accordingly, and for this case it is this direction, this one, this one. Now, you can see that when you calculate the curl of entire this mat and all this ds you calculate and then integrate it over, the final outcome is only this portion here. This is the final outcome, because this is the line which is not cancelling out by the curliness. Can you see that? All these terms that is sitting here, intermediate links, they are cancelling. I am having here also this. Except the boundary, all the intermediate region is cancelling out when you calculate the curl of the A, which is the measurement of curliness over these small regions, and at the end of the day these things is equivalent to the calculation of the entire vector field, the line integral of this vector field over this closed line. So, then these two things are seems to be correlated like this. So, these are the geometrical understanding. So, these things depends only on the boundary. Okay. So, eventually I can calculate only the boundary of this surface, the line integral of the boundary of this surface, and that will give you the same result if you calculate the curliness. Well, now we will going to prove this rigorously. We will have a rigorous proof. So, the statement of the Stokes theorem, once again let me write that the surface integral of curl cross A over a surface is equivalent to the line integral of this closed line integral, where the line is encircling the entire surface. Okay. So, this is a surface integral, and this is line integral, closed line integral. Closed line integral. Well, let me prove it like the previous way. We can also prove that, and let me do it here. So, this is the coordinate system I am having. Say this is my x and this is my y, and we can have a small block here, surface element, so that this is my delta x and this length is delta y. I can have a point here, the center P, which has a coordinate x0, y0, say like the before. Okay, and this is the direction of z, and this is along the k direction, that is the that for this surface, that is the direction of this surface, okay, the k. So, I can write it here. So, ds is the magnitude of ds here and with a unit vector k. Okay, now let me calculate A dot dl. Now, this closed line A dot dl, if I calculate, I can write it in these four lines. One line is here, another line is here, and this is the way I will go, because this is a line integral, I need to have a direction as well. So, this is integration of, like before, I have a x, okay, then x 0, and let us start with this one, this upper one. Let us start with this lower one. So, it is y 0 and then minus of delta y divided by 2. Okay. So, that is the x component of the vector field along this direction, because I am making a line integral, mind it, and then dx. Okay, that is for this line. So, let me write it 1, 2, 3, 4. So, this is my 1, this is my 2, this is my 3, and this is my 4. These 4 lines I need to integrate. So, this is line 1. Then I add the next one, and that is for say let us do that for 3. So, this is for line 3. There is a special reason I take 1 and 3 and 2 are 4, because they are in opposite direction, that is why. So, I have a x here previously the way we had, and then x 0, and now I have y 0 plus delta y divided by 2, because in 3 this is y 0 plus and dx. But at the same point you need to be careful that here the line is this direction and here the line is in opposite direction. So, that is why this sign should be a negative sign. Here we are having negative sign. In the similar way, if I add another 2, say plus integration of say line 2, for line 2 I can have a x and now x 0 plus delta x by 2 and y 0 and then dy. This is in the anti-clockwise direction. So, I am moving this direction. The other direction, if I consider, there will be a negative sign, and that integral will be simply integral, that is for 4th line, will be will be a x x 0 minus delta x divided by 2 y 0, and again changing parameter is dy over dy. Now, in the similar way that we had in the previous case, that expanding this as a Taylor series, I already did it, I am not going to do that once again. So, we will get simply this quantity. So, left hand side you are calculating closed line integral a dot dl, and what you are getting in the right hand side is this. So, if I just extend this Taylor series expansion, you will simply get minus of integration del a x del y dy dx, with the condition that delta y tends to 0, delta x tends to 0 for tiny, very tiny. And another term you are also getting, that is plus integration of del a y del x dy dx. What you need to do is just expanding. If you expand this quantity, so let me do for first term, the second term will be very straightforward. So, I am doing here. So, you are having a x 0, the first term, y 0 plus delta y by 2, y 0 minus delta y by 2. So, y 0 minus delta y by 2, this is one term, and then you have minus of a x 0 comma y 0 plus delta y by 2. Now, this quantity is a x 0 y 0 minus delta a, okay, this is a x. So, this is x delta a x delta delta y and this delta y divided by 2 and then minus a of x 0 y 0, there should be negative sign again. Previously there is a negative sign and now now we have a minus, and this will be a plus sign, plus delta a x dy delta y by 2. So, this term eventually gives me, because these things will cancel out like the before, and eventually I am getting minus of here del a x del y delta y, and now if I put delta y tends to 0. So, these things leads me del a x with a negative sign del y dy, which I already put here. So, del minus of del x del y dy, dx was already there. In a similar way you can get this. Now, if I combine these two, I can write it as del a x del y minus del a y del x and dx dy. Mind this, dx dy is nothing but ds. Okay. Now, if I go back to these this curl thing, curl of a ith element is epsilon I j k del j a k, that is the way we define. So, what is the z component of these things if I want to find? Z component will be simply epsilon z x y del a y del x, and then the non vanishing term will be plus epsilon z y x and then del a y del a x del a y. Okay. So, these things is with I mean, if I write, it is simply del a y del x minus del a x del y. This minus sign is because of this term, because it is anticyclic. Okay, so that quantity, if this is z component, so I can find that for I mean, this is eventually tells me that if I calculate the line integral, the closed line integral a dot dl, in the right hand side I am getting curl of a with its z component and ds. Now, ds is along, if I just simply put down this vector sign, you need to understand that ds is mod of ds and then k vector. So, exploiting that relation, and this is a z component, also we have a k vector. So, k dot k should 1. So, simply we can have that curl of a dot ds in vectorial form. So, you can see that that is the statement we are looking for, and we prove this, The left hand side we are having the closed line integral, and in the right hand side we have a surface integral where we are calculating the curl of the vector field and make a surface integral that should be equivalent to the line integral while the line is enclosing the surface. We prove this with this simple technique, and then you should make a look that all the I mean these proofs are very straightforward. I believe you understand that. In the next class we will do more about some identity using this curl, and these important identities are there. So, today's class are very important because we understand how the curl is operating over a vector field and what is the physical significance of that. So, with that note I like to conclude today's class. So, thank you for your attention and see you in the next class.